Okay, hopefully it's recording now. It was being a little bit weird. But it's been a minute since we talked about induction machines, but this is the continuation. So remember when we introduced induction motors, primarily induction motors, or any induction machine, the concept of an induction machine is contrary to a synchronous machine. An induction machine usually always has an AC rotating, not an AC rotating, a magnetic field that is produced by an AC set of currents. So whether it's a wound rotor, which we're essentially injecting three-phase AC currents into the rotor circuit, or if it's induced, where we get actual AC current flow because of the fact that we got coils of wire that are there, and we got a changing magnetic field that we see, and we induce a current, and that creates a magnetic field. In either case, it's going to have an AC set of windings. So a better term and a more generic term to call it as an asynchronous machine, because it operates on the concept of never running in sync with the AC phase currents or the magnetic field from the phase currents that are rotating along, meaning the mechanical speed doesn't rotate at the same speed. The magnetic fields always have to operate in sync with each other, but the actual rotor itself does not need to operate in sync. In fact, it cannot operate in sync. So an induction motor basically is two three-phase independent, right, not connected set of windings, one on the rotor and one on the stator, and they pass power back and forth. Kind of sounds like a transformer, doesn't it? That's essentially what a transformer is. You've got an AC winding, and I said three-phase, but it's really single-phase. You have a primary and a secondary and a transformer, and then you use magnetic energy to convert from the primary winding to the secondary winding to get that power flow. It's the same thing on an induction motor or an asynchronous motor. The difference is on the transformer, on our secondary winding is connected to the load, right? So we're delivering power to the load. Over here, there's a mechanical load. There is no electrical power that's being conveyed to something else. In fact, it's all mechanical power. So we can take our transformer equivalent circuit, all right, and we'll put a box here and a box here and a transformer and a transformer. And essentially, instead of current going out someplace else, it stays inside the machine. The current goes no place. So we'll take our equivalent circuit model for our transformer and apply it to our induction machine. It works exactly the same. The only difference is we have to have some sort of impedance or some sort of resistance that is representative of the mechanical load, right? That's the more difficult part about a motor is you do have a power output, but that power output is conveyed mechanically. But I can certainly go ahead and replace a mechanical motor load with a resistive load. Anybody buy that for $1? Anybody believe that? What is the motor rated for? 50 horsepower, 100 horsepower? Can I convert that to watts?
Yes.
What does the power consumption in a resistor look like? What are the units for that? Watts. So watts equals watts, right? So as long as I have an equivalent resistor, that is, again, equivalent to the amount of mechanical power out, the circuit works really well. So here is our transformer circuit, modified to be a motor. Yes, sir.
Do you have to do anything if there's like a efficiency there? Like if it's the mechanical load, that's the output power, right? So
that's the mechanical output. It does not, and this is a very good point that you bring up, Reed, it does not include friction and windage losses.
Okay.
Right?
Yeah.
That's separate.
That's not shaft output.
That's not shaft output, right? Unless you do have a way of saying, okay, here's the resistance, including all those shaft losses too, right?
Okay.
So if we said it's 100 horsepower, that's the actual mechanical torque that's available. But if we tweak that and add on, an extra horsepower or two to include friction and windage losses, bearing losses, etc., then we certainly could do that. Because again, the friction windage losses are just watts. So we can add resistors for that. Yep.
You just have to.
Yes. Yep. But we'll start to see when we discuss these, we'll make it a little bit easier. And so we'll ignore some of these stray losses to make it easier. All right, but the circuit is great. The problem is I don't really know the turns ratio. Because the turns ratio in a transformer is really easy, right? You can count the number of windings, make it really easy, and then you assume it's a pretty well coupled machine. So the turns ratio is really easy to calculate. Over here, it's very difficult. And part of the reason is because the frequency is unknown, right? This we know is 60 hertz. The frequency over here is a question mark because the frequency is actually dependent upon the operating speed of the mechanical shaft. So much more difficult to go ahead and calculate these effective resistances. Also, these impedances or these, the X and the R, those are water resistances, and those are hard to obtain as well. So we're going to modify that circuit. And we move, I don't know why this is not hiding itself. It should be hiding. Let's put this down. There we go. So our equivalent circuit is going to be based on our slip. That was the other concept that we discussed before break started, is slip is equal to, or is determined the ratio. So between the mechanical speed of operation and the actual synchronous speed of the machine. So slip is just another way to say what the difference between the two is. So let's look at sort of the extremes of slip. So when a machine is fully slip, which means its slip is equal to 1, that's the motor is not rotating. It's energized, but it's not rotating. And another way to say that is that's called locked or blocked rotor conditions. And what you're going to see is the absolute highest voltages and frequency. Why is that? Because remember, I have a magnetic field on the stator that's rotating proportional to 60 hertz. The actual rotor itself is not moving. And since the amount of voltage and current that you're going to develop, really it's current that you're going to develop, is based on the rate of change of the magnetic flux, the rate of change is going to be the worst when this is equal to 0, right? Because the other thing is spinning around at 60 and you're not moving at all. So maximum current, maximum voltage you're going to generate. So that's going to be the highest value in terms of voltage and frequency that you're going to experience. What about at synchronous speed? What if the rotor is operating at synchronous speed? What kind of current and voltage will you be generating on the rotor? Very good. None, because you have no difference in speed. If this is operating exactly the same speed as that rotating magnetic field, there is no changing magnetic field, right? Again, you only induce a current when you see a changing magnetic field, just like in an inductor. What happens when you put DC to an inductor? Not a tough question.
No, after a steady state, it acts as a short.
Yeah, an inductor looks like a short circuit in steady state. Why does it? Because it's no longer generating a voltage to oppose the changes in current. It's fixed, doesn't matter. So it's exactly the same thing for a motor, an induction motor. So you're not going to generate any current or any frequency. You get no voltage. So the other extreme is 0. So let's go ahead and develop a voltage, and we probably have some ability to detect this or measure this. And this is going to be our ER0, which is our worst case lock rotor voltage. And we're going to assume that as our slip changes, right, as it decreases, it goes from 1 to 0, that our voltage is going to drop proportionally. And so if we do that, sorry. If we do that, geez. If we do that, then we can say that our frequency is going to drop as well. So our voltage, go back over here. This is our actual voltage that's going to be on the rotor circuit. It's a function of the block rotor voltage multiplied by S. And our frequency is also going to be based on that same ratio, right? At 60 hertz, you're going to have the maximum frequency and you're going to have maximum voltage. By the way, does that make sense based on our concepts of what happens in terms of generating an AC voltage? Well, I keep harping on this, and I'm doing it subtly now. What did we say about the speed of operation of the two magnetic fields, the one on the stator and the one on the rotor? They operate in sync with each other, right? So if the stator frequency is operating proportional to whatever the 60 hertz conversion is, the rotor frequency also has to operate at 60 or proportional to 60 hertz. And if you recall, when we talked about induction motors, the fact that the induction motor, it's spinning at a speed, so the difference between the stator magnetic field and the rotor magnetic field, it makes up that difference, okay? So essentially what you have is you have something that's rotating along, let's say it's 30 RPM, the electrical frequency has to be the equivalent of, you know, not 30 RPM, but half the speed of what the proportional was. So let's make it 1800 RPM. And it should be 3600 RPM. Then that rotating magnetic field that is produced by the rotor, I mean, the rotor current flow should be equivalent or rotating equivalent to 1800 RPM. Because again, it's got to make up the difference between the two. Well, in this case, under locked rotor conditions, that's at 0. So shouldn't it be operating at 60 hertz? If it has to be at the same synchronous speed and that rotor is not rotating at all, but the rotor has to make up the difference between what the rotor field is operating at and the synchronous speed is operating at, then it has to be 60 hertz. Okay? So this is way important to see that the electrical frequency on the rotor is going to be the difference between synchronous speed and actual mechanical rotational speed. All right. So these used to be, back before we had semiconductor devices, they used to be things called rotary converters. A rotary converter was a variable frequency drive, essentially, that you could get different frequencies out of. So you would just monkey with the speed of operation of the rotor. And if you had a way of pulling off the AC out of the center, you've got a variable frequency drive. Very expensive one, right? Not very efficient, but that works really well. So now we're going to see how this applies to our XR that we had on our rotor circuit. So we know that X is equal to omega L or 2 pi FL. Our rotor impedance is just omega R times LR, which is the rotor frequency times the actual inductance of the rotor. Now I want to substitute in my slip and my frequency that I got from over here, right? Because that's the actual frequency of the rotor. And I just want to make it proportional to the electrical frequency. And then I see that that's 2 pi SFE times LR. Why don't I go ahead and combine these three elements and call that XR0? Now you can say, hey, wait a minute. I actually combined 4 elements. I also combined FE. By the way, why did I combine FE there? Why am I doing everything in terms of FE? Remember with circuit analysis, we assume AC steady state conditions. If we have one system that's operating at 5 hertz and another one that's at 60 hertz, you can't analyze them using steady state circuit analysis. So by introducing this S term over here, it allows us to use an electrical frequency of 60 hertz, and we get the results that we need. All right. That XR0 is just that blocked rotor or locked rotor inductance that we would do. We could calculate when we're under blocked rotor conditions. And so now here is our rotor equivalent circuit, all written in terms of 60 hertz land and written as locked rotor values. Okay. Here's our voltage. Here's our inductance. And our rotor resistance is not frequency dependent. Boy, excuse me. So it doesn't matter. All right. So we're going to modify our circuit to include that. So now we can calculate our rotor current, which is the current going through the rotor, which is our rotor voltage divided by R sub R plus JXR. But now we're substituting in our block rotor conditions. And we just make one little tweak. So if we want to find an equivalent circuit from the actual rotor circuit to everything reflected to block rotor, you will note that I want my rotor circuit current to be the same. The only modification I need to make is to divide my rotor resistance divided by S. And that's because I've got an S here, an S here. I can divide everything by S, right? Which means I have to divide that by S. So that where that term comes in there, okay? So now here is our updated circuit with everything written as a relative to a block rotor condition. And the modification we needed to make was R sub R over S. So let's look at this. Well, let me see. Let's look at this. Let's go back over here. This is a better way. Let's look at this for a second. Does the R sub R over S make sense to you? What I mean by that is, mechanically speaking, if I'm delivering mechanical power, what's happening? Well, what is this value of slip when the machine is running at synchronous speed? They're running at the same speed. What does S equal? Equals 0. RR divided by S when S equal to 0 equals infinity. Anything divided by 0 is a really big number. How much current flow do I have when R sub R is equal to 0? I mean, R sub R over S is equal to infinity. I get no current, right? Didn't we say when this thing is running at synchronous speed, it's just a hunk of iron that's rotating along? It doesn't have any magnetic field. So I get no values there, none whatsoever. How about the case when S is equal to 1? Now this value becomes R sub R. And if S is always going to be between 0 and 1, I'm going to get maximum current under the case under block rotor or locked rotor conditions, which is exactly what happens with real world induction motors. The moment you energize an induction motor, it pulls the maximum amount of current. Then as it starts to speed up, it actually reduces the amount of current, which is kind of opposite, right? Because there's no mechanical torque when the machine starts up, right? Because it's not spinning, so you can't have any torque. But in fact, because of the way the circuit is set up, you are generating maximum current through here, which means that rotor gets hot really fast. So you can't energize a motor and leave it in that locked rotor or block rotor condition for very long, because you'll actually burn up the rotor very quickly. Okay. Now there is one goofy thing about this, and this is just a personal story. I can say this is a long time ago. I did a project for something called the Architect of the Capitol, and their responsibility was to do the congressional record. So every day they'd print out 10,000 pages or whatever. They might not be necessarily more because everybody's got iPads and whatever. No legislator is walking around with thousands of pages of documents, but back in the day, that's what you did. And so the Architect of the Capitol had they wanted to do an electrical evaluation of their system. And so they asked me to do it. And so one of the things that I did was look at their entire electrical system, including their fire system. And they had a fire pump on there. And I can't remember if it was a 5 or 10 horsepower motor. And I looked at the protection for the motor, and it was set so that basically the motor would never trip because of heavy current. I'm like, that's nuts. Why would you do that, right? There's no protection. And then I started reading in the National Electrical Code. Does anybody know who produces or issues the National Electrical Code? It's NFPA 70. Go ahead, Taylor, sorry.
So I said NFPA, right as you said it.
All right, you can answer this one then. What does NFPA stand for?
National Fire Protectors Association? National Fire
Protection Agency, right? Their job is to prevent fires. Somehow, they ended up owning the electrical code. But back in the day, the electrical code was put in place because there were so many fires happening from the National Electric Code. Since then, the National Electric Code has become way more about safety and added all these other things. But why does the fire pump get to run indefinitely, even if it damages it? Because if a fire pump is running, what does that normally tell you?
There's a fire.
There's a fire, exactly. And so the thought was with the National Electric Code is it's more important to put water wherever it is, wherever it's needed, right? Because this was charging up the water lines for the sprinkler systems. Wherever that water is needed, I don't care. That let it burn, basically, is what the National Electric Code says. Keep that fire pump running. Do not let it trip offline, because even if it's going to get damaged, it's still better to replace a damaged fire pump than it is to let the building burn to the ground, I guess, type thing. So, yeah, that's the only time, again, that I've ever seen where you actually have protection set on an element to basically not protect it. So you would set it above whatever it would draw in the worst case conditions. So that it provides no protection for the motor. It protects the circuit going to the motor, but it actually doesn't protect the circuit. No, but it doesn't protect the motor. So now we'll take our transformer circuit and we'll move everything. We'll move everything to the primary side. We don't have to worry about a transformer. And we can't because we don't know what the turns ratios are. So I'm just going to include all these in here because I have no idea what they are. And then I'm going to write new values for my impedances. X2, R2, I2, E1. So these are reflected impedances onto the primary side, not worrying about the transformer. And now I have a beautiful equivalent circuit. So I can model this and I can examine it and do what I need to do to make the circuit analysis or whatever I need to do work really, really well. So this is kind of going back to Reed's comment or question about losses in the machine. So we had those power loss equations. So in a transformer, we had winding losses. How about I squared R losses, right? Those are in the stator. I1 squared R1. We also have rotor copper losses in the rotor winding, and those are I squared 2 R2. But the question is, where do you see R2? I see R2 over S, but I don't see R2. And we said that R2 over S is proportional to the output power. Well, sort of, right? R2 over S. What does R2 over S equal? What's that?
They're not law.
How about that? Can you do the algebra? Let's put it back, all this back under a common denominator. So if I put everything back under a common denominator, this is R2 times S plus R2 minus R2 over S. Isn't that the same when you're doing your math? So I can break this up into two resistors. One is R2 and one is R2 times 1 minus S over S. This is the I squared R winding losses. What's this equivalent to? There's no more losses, right? All the winding. So this is going from stator to rotor. So I don't have any electrical losses left once I dropped the I squared R losses out of the rotor winding. So what would the R2 times 1 minus S over S equal? Yeah, that's P mechanical. So remember, our mechanical engineering friends are only using this motor because they need drive torque. But electrically speaking, we need to provide enough input power so we can drive that mechanical load plus all the losses in the machine. So we just characterize those losses in the machine as including the loss because of the power consumed, if you will, or provided to the mechanical system as R2 times 1 minus S. And now we can finish with this, right? So we have I squared R, primary, rotor and stator, secondary and primary. We also have core losses. What do you know? Just like in a transformer. Now we have some mechanical power losses, but those are downstream, right? So all after here, now I have to start subtracting friction and windage losses. And here's our diagram. Here's our input power, square root of 3 VI cosine theta, right? Which is the same thing as saying S equals VI conjugate and then pulling the real part out. Now I drop out my stator copper loss. I drop out my core losses. And at this point, the power that has taken out has all been all the power that I need to consume in the stator circuit has been consumed. Now that power that is available to me can jump across the air gap via the magnetic field and do its work on the stator. So that's why we call that air gap power. That's literally the power that jumps through from the air gap, from the stator to the rotor. Now I got a couple losses because of my R2 value that I have over there. So I'm going to subtract that. And then everything else at this point, as Reed had mentioned previously, is all mechanical power. So instead of calling it mechanical power, because mechanical power, and this is where we have to help make sure that we're talking same terminology between electrical and mechanical. Mechanical power to me, if I'm a mechanical engineer, that's shaft power, I would think. So electrical engineers don't call it mechanical power. They call that converted power. That is the power that is converted from electrical world to mechanical world. Not mechanical or output shaft power, because I still have to drop friction and windage and any stray losses. And this is the actual output or mechanical power that I can drive my load with. Okay? These terms are super important that you understand them, because if you don't, it'll make it really hard to do some of the calculations. Because PN is very different than P air gap, very different than P converted, and it's very different than P out. But more importantly, you have to understand when we're talking about an induction motor or an asynchronous motor, where do we lose power, or where does the power get taken out to go ahead and create each of those powers? So we'll summarize here. Here's P air gap, PN, VI cosine theta, square root, or times 3, depending if you use line or phase quantities. Stator copper losses are I squared R. Can we use V squared over R? Sure. But remember, if you're going to use that, you need the voltage drop across VR1. Don't include this voltage here, because that's the total voltage drop across the machine. That's not the voltage drop across the resistor. So that doesn't work. My air gap power is equal to my input power minus my stator copper losses and core losses. You can see that from the figure. Then I have converted power. So I take my air gap power and lose the rotor copper losses. And then my output power, the actual output power, is that mechanical converted power minus the mechanical losses. Okay. These are mechanical losses. And so if you have to do analysis, you got to go talk to the mechanical engineers and say, what are the mechanical losses of the system? Unless you can calculate bearing losses. I don't know if people can do that easily or not. I don't think it's that easy, but maybe it is. Because the bearings, right? There has to be the smoothness of the bearing. That's a big part of it. Also the lubrication in the bearing. That's a huge part of it. And then the friction and the windage. The windage part of that is how smooth the shaft is. I don't know if anybody's ever seen what an induction machine shaft looks like, but it's not the smoothest, right? It's an iron, kind of rusty because it's just made out of iron. but it isn't perfectly smooth. You know what I mean? You can rub your hands on it. And I'm not saying it feels like sandpaper, but it's not polished like a mirror where your hand slides right over it. So you can polish your shaft if you want a little more efficiency. And then my induced torque, the actual torque that is available. And again, this is to drive all the mechanical loads, not just not the mechanical, the friction and windage losses, stray losses, and the output mechanical demand is going to be calculated from there. So it's the actual power equals torque times omega. So converted, which is mechanical power, divided by the actual speed of rotation is equal to my induced torque. And we'll talk about how to calculate how we can get P air gap and omega sync here in a little bit. So I put together that R2 and broke up the figure. This I find to be a lot more useful when you're understanding or trying to understand what's going on in your circuit. But this actually requires a little more work because I have two voltage drops that are independent from each other, right? So when I'm doing a loop equation, I just have to include one additional loop. But the rest of the circuit remains exactly the same. The combination of these two is equivalent to R2 over S. Same thing. So more relations. Again, this is just writing it slightly differently. So we've already gone through this one and this one. We started with this one, but we know that the air gap power is also going to be equal to the converted power plus my rotor copper losses, right? But that is the same thing as I squared times R2 over S, isn't it? Because that's the total mechanical power. Sorry, converted power. So if I substitute R2 over S, I'm close. The only difference is that instead of 3I2 R2, I have 3I2 R2 over S, which means if I want to calculate air gap power, I can take my rotor copper losses and divide by S. Okay? Make sense? You can just divide by the slip, and that actually tells you what your power, air gap power is going to be. Then I continue on. So here's just my standard rotor copper loss. Now my actual converted mechanical power is subtracting the two, and there you know. This here is that 1 minus S over S. So the ratio between the two, right? So I have my rotor copper losses here, and my converted power is over here. So this is equal to just that 1 minus S over S. That's what I have right here. This is R2. This gives me P rotor copper losses. This is also P rotor copper losses, but now I multiply it by 1 minus S over S. All right. Now, why is this important? Because if I make this substitution, that I see that I've got air gap power, which I got from here. I have my P rotor copper loss. So this is P rotor copper loss over S minus rotor copper loss. I can go ahead and I can substitute in this value. So I get P converted is equal to 1 minus S times P air gap. Why is that important to me? This is a very important equation. It tells you a lot about something really, really important. Think about it.
It's driven by the slip speed.
Keep talking.
Well, if you can, get the slip speed to equal 1, you'd have no air gap loss.
If the slip speed is equal to 1, which means it's not rotating at all, you don't have any mechanical power out, right?
Right,
What about the other extreme?
right.
If it's 0, it actually doesn't work, right? But it tells you something. What happens when the slip is almost 0?
You're gonna have the most air gap loss.
Air gap loss? Go ahead, Reed.
Tells you how much air gap, how much power through your air gap is actually getting sprayed with the weight.
Say that again, louder.
It tells you how much air gap power is actually going to convert it to useful work.
So for those of you in TV land who can hear him, I'm going to paraphrase. It tells you how much air gap power gets converted to real work. Isn't that a kind of another way of saying efficiency? Because my air gap power has to have rotor copper losses plus mechanical out. If all my air gap power went to mechanical power out, right, that'd be a really efficient system. So with that being said, where do you think you tend to operate these machines? As fast as possible, as close to sync speed as possible. So let's look at some nameplates for some induction motors. Let's see. Let's see if we can find some operating speeds. Let's just pick one here. Asynchronous motor. So this is a 50 hertz one. You could do it if you wanted to, but it needs a little more calculation. We want to use a 60 hertz. All right, 60 hertz machine here. RPM. This one only runs at about 1700. Not very good. And not a very efficient motor. Let's look at this one. This is a, let's see, where's the speed?
Does that mean it's 90% efficient?
This is a 90% efficient at its full load speed.
Oh.
This is a 50 hertz machine, so we don't want this one. Try to find one that's kind of new. 60 hertz machine. This is only 90%. That's pretty low. But this operates at 1760 RPM. So this is probably a 4-pole machine, right? That's operating darn close to its synchronous speed of 1800 RPM. Let's take a look now and modify this. Let's see the premium efficiency ones. If I can type.
Ooh, those are spendy.
But they're not super crazy expendy. Let's see. See the new ones, like the Baldor, the Reliance. Let's see if this one has any. Energy efficient. I don't know if that counts for anything, but where's the frequency here? So this is 1785. So the other one was 1760. So these operate, this is a energy efficient one, and it's operating really close to 1800 RPM. So most of the motors today run very, very close to their synchronous speed because they want the highest level of efficiency. You don't want a motor just chewing up I squared R losses in the rotor for no reason. In the stator, there's nothing you can do, right? Because you got to move power to it. So that is what it is. But if I can decrease the amount of current that flows in the rotor circuit to deliver rated torque, then I save myself some rotor copper losses and I can get higher efficiency. So what's that?
So that was pretty powerful, 150 horsepower.
Oh, that's small potatoes. There's much, much bigger ones than that.
Oh, sure, but still, it's got a lot of
It's
bang.
powerful for most normal human beings, but if you're in an industrial facility, 150 horsepower is not all that big.
No.
So, but yeah, motors want to run at higher levels of speed or lower levels of slip so that they have the most efficiency. And then again, the P outs, P converted minus the mechanical losses. We can substitute in P converted for 1 minus S over P air gap. Same thing for omega sub M. And what do you know? That's the equation that we got on the first page. Okay. So here's a really good diagram. Shows the power relationship. If I have 1 unit of power coming in through the air gap, 1 minus S of that power is converted to mechanical power. and S is dumped as heat. All that says. You can see all the energy loss just by looking at this diagram. Okay. All right. So let's take a look at example. 480 volt, 60 hertz, 50 horsepower, three-phase induction machine. It draws 60 amps at a 0.85 lagging power factor. I've got stator copper losses at 2 kilowatts, rotor copper losses 700 watts, friction and windage losses 600 watts, and core losses are 1800 watts. We'll neglect any stray losses. So find those 4 items. So I don't have an equivalent circuit to work with here, do I? I don't know what X1, R1, X2, and R2 are equal to. Those are all unknown. So I can't use the equivalent circuit. But what I can use is this diagram here. Right? I'm told everything in terms of power. So if I go back to this diagram, I'm actually able to calculate all these parameters. Okay. So the first thing we're going to have to do is do a power triangle with this and this, right? Actually, no, not this and this. What is this right here? That's a nameplate rating. Is it delivering 50 horsepower? Who knows? We don't know. I do know that it's drawing that much current. And if I do S equals square root of 3 VI conjugate, that's going to be a P plus JQ. I am able to compare somewhat those things. Why not exactly? This is P out, isn't it? This is P in. So I could compare it if I actually had an efficiency number here, but I don't do that. So the first thing I got to do is calculate P in using that equation over here. Then I'm going to take out stator copper losses, right? And that's going to get me my air gap. And then that power has to have its rotor copper losses subtracted. Now it's mechanical power. Now I take out friction and windage. Actually, I got to take core losses out first to get air gap power. So my air gap power is going to be equal to P in. Let's just write it down. Minus P stator copper loss minus the core losses. My converted power is going to be equal to my air gap power minus my rotor copper loss power. My output power is going to be equal to my converted power minus my friction and windage losses. And my efficiency calculation is going to be P out over P in. Okay, just take P out over P in. That's how you calculate efficiency. So let's see that. Square root of 3 VI conjugate, or if you just need to go ahead and use the real power calculations, you can just simply go VI cosine theta. So 42.4 kilowatts. My air gap power, I take out my stator copper losses and my core losses. So now I'm down to 38.6. Now my converted power is the air gap power minus the rotor copper losses. I'm down to 37.9. My output power, I take the converted power, subtract friction and windage losses, and I get 37. And just for giggles, because the problem description that we had initially was 50 horsepower, but I said that is not necessarily what it's producing for power, but it's drawing 60 amps. So that's what electrically it's doing. We see that we're drawing 50 horsepower out of the machine. So this machine, and if we went back to here, hard to see, but let me see if I can annotate here real quick. If you look at the machine, right, this is as Arthur said, it's a 150 horsepower motor. Where's the, right here? It actually tells you the current. So to deliver 150 horsepower, this machine draws 163 amps at, what's the voltage? Must be 480. Yeah, or 460. It doesn't tell you the power factor, I don't think, on this, does it? Show it here? Actually, no, it does show the power factor. You can see it says 89.7. So let's check their results. So we have 460 times the square root of 3 times 163, I think was the current value,
Yes.
times 163. Why is this not doing that? And then I multiply that by the cosine of theta, or the power factor, which is 89.7, 0.897. And then I divide that by 746. Does that equal 150 horsepower? Anybody know? I can bring it up on MATLAB. I think I have MATLAB up.
What was it? 0.897 by 746, 156.16-ish.
I get, unless I did it incorrectly, I get 116. Did I do something wrong?
I don't know. I did the square root 3 times
Oh, I
4.
forgot to divide by 746.
Yeah.
Yeah, so 156. So, I said 150 horsepower, but this is actually 156. I screwed up, didn't I?
Tolerance.
I'm blaming my mechanical engineering friends. They should have used much better bearings. They should have used much smoother shaft. That is the current, that's the converted, right? You still have to do friction and windage losses. So what this is telling me is that to provide 150 mechanical horsepower shaft, that this actually produces 156. So there's about 6 horsepower of losses in the machine. Okay. So if you were to divide 150 by the answer, this is a 96% efficient machine. All right. And let's compare with a nameplate. Do you see 96%? I put 96.6. They put 96.2. They don't know how to use MATLAB. But pretty cool, right? You can actually see all the stuff we're doing in this class. And I just pulled this random one, this nameplate out from wherever. I didn't, go looking for it in advance. I just brought it up randomly. So you can see how those calculations are there. So around 4% of the input power to a motor is lost. And that's a lot, right? 6 horsepower times 746, you're talking a continuous 3 kilowatts of loss. So you're just blowing away 3 kilowatt hours for every hour this machine operates like that. Doesn't sound like a lot of money, but if the machine runs 24/7, 365, that's 75 cents times 24 times 365. Starts to cost a lot of money. So you can't look at these as, oh, it's only 75 cents. It's no big deal. No, these motors run long periods of time. So it does oftentimes make sense to go with a premium efficiency motor if you can do it. All right, let me clear my annotations because you get the idea. And that is your first example of how to do basic power flow diagrams with 3-phase synchronous motors. For the next class, we'll actually go back to this equivalent circuit and actually do circuit analysis with it. So for the next class, you have 2 ways to do it. You can either do, so let's go to the actual circuit here. You can take this circuit right here that we have and do parallel series combinations. which is fine. But I like to do mesh analysis, because with mesh analysis, I can solve for I1 and I2, and I2 is the equivalent rotor current. I1 is the stator current, and I can calculate all those losses very readily in my machine. So you may, over the weekend, may want to brush up on doing mesh analysis in AC circuit land, because it's pretty helpful to look at these circuits from there. All right, party people, questions? I know it's been a minute about induction machines, but again, the key thing about induction machines, they can never run at synchronous speed unless you externally drive them. If you're pushing them to run at synchronous speed, then really it's just a hunk of iron you're rotating. It's not rotating as a motor. At that point, you might as well switch it off. But that variable AC frequency we have works really good for wind turbine generators, right? Because think about a wind turbine generator. Is it running at a constant speed?
No.
No. Once they get to a certain wind speed, then they will try to run at that constant speed. But the likelihood of it staying at a constant wind speed is pretty low, unless you're really, really high up in the air and perhaps offshore. Like being offshore, usually you get a more consistent wind resource. So in those cases, you actually get pretty good resources, but still you do have some variability, but we still need to interconnect to 60 hertz land. So the fact that you can run a wind turbine generator at different frequencies and still be connected to 60 hertz is the biggest reason why you see so many wind turbine generators that are using, they call them doubly fed induction generators, but it's basically using the same concepts that we have over here. And so one of the things we talked a little bit about at the first class was what's a wound rotor induction machine. The only reason why we talked about that is because you use them so often in wind turbine generators. Otherwise than that, you don't need doubly fed induction machines for speed control, because you can buy a variable frequency drive. And somebody, I think it was in this class, was asking me, you know, how do I get these speeds? You can go to Automation Direct, and you can buy VFDs from Automation Direct for very, very little, surprisingly little amount of money. So let's do variable, let's do micro. I don't know if that's important. And 134 bucks.
Could you share your screen there?
Oh, I'm sorry. I forgot I was not sharing my screen.
Thank you.
Yeah, so this website is Automation Direct. And I just clicked on some of their drives, and you can buy, you know, $119. These are micro ones. And I don't know what size, but this one can go up to 1 horsepower for 134 bucks, maybe. I mean, I don't know all the spec sheet stuff, but you can get these really cheap. And ABB, I'll show you this one as well. So I had to specify a bunch of these in my previous life. You used to be able to buy medium voltage drives. And these go up to 100 megawatts. I don't think you'll get pricing information on those, but they can run up to 15,000 volts. So, you know, pretty big cabinets, but you can have 1,000 horsepower. I think the biggest one ever specified is 1,000 horsepower VFD. But remember how we start gas turbines, right? We can't start synchronous machines across the line. So if you go over to just down the road in VZ, there's also the same thing in Westbrook. If you want to start those gas turbines, you can't just light the fire and let them go, they'll burn. So they've got to go ahead and start. And those are 150 megawatt generators. And so conceptually, you could be almost pulling, you know, 150 megawatts of power through that. So these generators, these variable frequency drives, you know, this can go more than 100 megawatts. So if you needed to start a big gas turbine, you could go to ABB and buy a medium voltage drive, because they have the capability for it. Not saying it's cheap, but you can buy them. So yeah, this is where our mechanical engineering friends, this is And you can start to see a little bit of it too, because back in the day, I mean, mechanical engineering was where everything was at, because that really dictated. We did everything mechanically. But now we can do a lot of things with semiconductor devices, and we can really, really improve the efficiency. So if you worked at an industrial facility, everything used to be motor operated valves, maybe had a few pneumatic valves to kind of control things. Those are switching to electrically operated valves because you apply electricity and it goes in its position and it's happy to stay there. Air, you need air lines running all over the place. They can get leaks. Electricity, you can use diagnostics. You can do all kinds of different things. And so you're getting more and more efficient. Even cars, right? I was talking to somebody the other day. I have a 2010 Toyota car that has the steering has no I don't have a pump for it. It's all electric assist. So there's a little electric motor that helps when the car is going at low speeds to turn the wheels. Does anybody here have a car, a newish car that has a power steering pump in it?
No, the motor on mine is on the rack and pinion under the car. Yours is actually on the steering column, if I
Yep,
recall.
mine's on the steering column, yep. But it used to be that you had a serpentine belt that would drive all these accessories in your car, because like, what are the power assists you need? You know, for a small car, maybe you can, and I used to have a small car when I was much younger, but I had to turn it by hand, but cars used to weigh 1,600 pounds. They weigh three plus 1,000 pounds now because of safety. But if you have a 1,400-pound car, turning the steering wheel was not that big of a deal. You also had 14-inch tires that were really thin, so things are a little bit different than your 19-inch super wide tires you have today.
You mean like that old VW I just pulled out of the garage with pizza cutters on it?
I'm not going to do that. I'll let you defer. I'm not putting anybody down. I'm just saying my own experience. But yeah, that might have been manual steering. How about brakes? Brakes operate a little bit differently. They operate on a vacuum. I don't know if there's a vacuum. There must be some sort of a vacuum priming system for the brakes, but I don't quite know how that gets it.
No,
But-
there's the modern ones, the ABS module has a electric pump in it to pressure to assist the pedal.
Yeah, pressurize the system with the brake fluid.
Yeah.
And why do they do that? Because if you're not running the brakes, why would you run a pump to help with vacuum when you're not applying the brakes? So
Well, there's also an issue with modern cars that the manifold vacuum is not really enough to operate them anymore.
okay. So yeah, the joke was if you looked at old cars that had, you know, air conditioning and power, this and that, you had serpentine belts that would go on all these different places because they got their power from the rotation. Now in modern cars, even the fan for the radiator is electrically driven. Why is it? Because what if it's not hot outside? You might not need to blow air on the radiator to cool it. So the car will monitor the temperature of the antifreeze and make a decision. Yeah, we get to blow air, we don't blow air. So it's a more efficient car. So just by changing a couple things from the old ways of everything had to be mechanical to making them electrical has resulted in massive improvement in fuel economy. Got way less those are called parasitic loads. They're not doing anything useful, so that would be a parasitic load. Where does a parasitic come from?
Parasite.
Parasite, yeah. It's sucking energy from the host that it doesn't need to be there. So that's why you'll hear the term parasitic loads. So okay, I'll shut up now. Any questions?
What would be a good use for like inductive motors versus like a brushed motor?
Almost any induction motor, you'll see the application in an industrial environment because you can get fairly constant speed depending on the load, and they're incredibly cheap, easy to make, are very reliable. So by far, any industrial application, you're almost always better off to go with a three-phase induction motor. You can go with a permanent magnet. Like if efficiency is really at a premium, like if you're driving a car, you know, they might maybe want to do something a little bit different because now you need every watt to squeak a mile or two out of it. But in an industrial facility, it's not worth the fact that it's a less reliable, more expensive piece of equipment for, you know, a 0.2% improvement on efficiency.
I see.
Okay, anything else? All right, hope you have a great day and try to stay dry with the nice rainy weather we have. Take care, everyone.
Yeah, it's freezing rain down here. That's why I didn't drive up.